Again, thank you all for coming. So I just want to recap. We have essentially been talking about this high-dimension estimation, and we discussed Lasso in some length, and we established some good properties about it in this high-dimensional context under, I would say, mild design conditions. So if some good event happens regarding penalty choice and the effective noise of the problem, we obtain nice prediction norms, rate of convergence to prediction norm. And we also talked about post-Lasso, which is just the least square estimator applied to the components that was selected by Lasso. So it allows for this data-driven choice of which variables matter. And then we also analyze the sparsity of Lasso. And if you had this condition that the maximum, let's say, S log n sparse angle value divided by the minimum S log n sparse angle value, if this is bounded, as n goes to infinity, as n grows, with high probability, we have that the size of the support selected by Lasso is bounded by a constant times the size of the true support. And the prediction norm for post-Lasso actually become square root of S log P over N, which will be the same rate for Lasso. So under nice designs, post-Lasso, which is a device to try to remove bias, remove the shrinkage after you select the variables, achieves the same rate convergence as Lasso. So, and up to this point, we have been talking about prediction. And I would like, would mention, in my view, the vast majority of this literature focus on prediction problems. That was, I think, the natural first step that for one to understand what you can recover. And today, and probably tomorrow, I want to talk about building confidence regions for some parameters with appropriate coverage. So I want to be able essentially to build confidence intervals. In particular, I want to build confidence intervals. In this high-dimensional setting. So this is a slightly different problem, and I want to try to understand what are the issues associated with that as we go. So I want to focus on a simpler kind of a first case, which might be the most relevant case. It actually is the most relevant case in econometric applications. So I want to focus on the following model. I have my outcome of interest, and I have a treatment. So I care about a treatment. And we can think about different examples, but I have one variable that's special, and the treatment I will call D. And I have the impact of the treatment. So alpha naught is going to be the treatment effect. many people think about the treatment being discrete, 0, 1, but here I will make no such assumption. The treatment is going to be continuous. And I also have extra controls. So I want to control for these confounding factors. So those are my controls. And I have my random noise. And I'm going to make assumptions on the noise as usual. The expected value of the noise given the treatment and all the controls is 0. And for now, I'm also going to assume a homoscedastic model. It's not too hard to relax that. But this is the model I want to focus on. So my whole goal here is to estimate this treatment effect in the end of the day. Essentially, I want to build confidence intervals for alpha naught. Now, the very natural first step on this was, okay, so I want to build confidence intervals, so I am in the business of chasing beta naught. So the first thing that people pursued was I want to find some estimator, let's say, of beta hat, such that the support of beta naught, of beta hat, equals the support of beta naught. And that's what people have been doing for a long time. That's kind of the mindset that, if you want. So what people typically do, especially empirical work, they will do a version of post-Lasso, or essentially, you find a way to select some variables t hat, and that can be done by very different things. And then you run least squares of the outcome on the treatment, because the treatment always going to be there because you care about the treatment, and the controls of the set that you selected. Right? So and that is kind of mainstream applied work. Basically, what typically people do is to run regressions, look at p-values, right, and keep the variables which have low p-values. Variables with high p-values, you just remove them. And I'm really thinking now, this will be the case that p is less than, kind of much smaller than n. Right, so that is already of interest. When p is bigger than n, then you don't have p-values. And then you can try to do model selection.
So just to make sure it's out. So what you just said is just do regression and
could be, you can think about some sequence of t-tests, for instance. But I don't want to actually constrain the method. Find a way to find your model selection procedure. In the case that p was much bigger than n, or like for these high-dimensional problems, people have been proposing penalties which try to achieve this perfect model selection. So I mentioned yesterday that under some condition, under some kind of not so mild conditions, Lasso could achieve this perfect model selection. But I think Fan and Lee in 2001 proposed this SCAD estimators, which you have penalty functions that look like this. So they can achieve perfect model selection under weaker assumptions, according to the analysis. Then came, I think, Zhu, 2006, proposed adaptive Lasso. And what adaptive Lasso does is that, okay, my the adaptive Lasso estimator is going to be similar to Lasso, but instead of using the L1 norm, it's going to use a weighted L1 norm. Where the weights I'm going to get from a first stage estimation, let's say Lasso itself. And the weights will be essentially 1 over the Lasso estimate for that component to some power. So the intuition will be that if the coefficient was very small, this extra weight will be very large. In particular, if this is going to 0, this weight will be going to infinity, and then I will not use this potentially this component in the next step. Only big components for Lasso that would have this low weight, and they will be preserved. That was kind of the idea of the method. And it provides conditions under which this also achieves perfect model selection. And then that generates this literature which is based on the oracle property. So for now, I want for you guys to think about P fixed. And the next theorem is going to make it clear why that's the case. So think about P fixed, and so essentially I want X transpose X over N going to converge to some well-behaved matrix, some kind of positive definite matrix. And then I'll suppose the parameter theta naught, which is just alpha naught, beta naught. I'm just piling those two parameters as this theta naught to make my life a little bit easier. Suppose whatever method you are using, it has the following property. The limit as n goes to infinity of the probability according to theta naught of the support selected by your estimator equals to the support of beta naught. That goes to 1. So what this is telling you? It's telling if you have, with enough observation, fix the model, if I have enough sample size, your method can identify what is in the true support from what is not the true support, having enough observations. For every theta naught, right? And theta naught. So I'm going to say that I'm only going to look at models which these vectors are bounded. So if you have this oracle property, then this procedure, which is running least squares on D on this selected support, and let me call this alpha, I don't want to check what I want to use here. How about alpha bar, which is the, so, and this here gives you alpha bar from this least squares. Then alpha bar from this procedure, which is this post-selection procedure, is such that square root n alpha bar minus alpha naught converges to, after proper rescaling of some variance, some standard deviation, to a normal 0, 1. So this should not be surprising. So if I'm assuming the oracle property. So with probability going to 1, I'm selecting the true model. Then if I run least squares of the outcome on the treatment and the true model, I get asymptotic normality as usual. That's kind of fixed P, just the usual least squares problem. So essentially what this is saying that, look, if you can identify perfectly what is 0 and what's non-zero, model selection doesn't really matter now, because I found the true model, which is, the true model is not data-driven, it's fixed, so I can go ahead and do asymptotics as usual. So let me rewrite this in a different way. So this statement is equivalent to the limit as n goes to infinity of the probability according to P naught of the distribution, and here I'm going to run out of space, so let me go to the other side because so that statement is, I want to just note as the limit n goes to infinity of the probability according to theta naught of the distribution of this estimator, this whole thing. I'm going to denote by f hat n. That distribution minus this normal in some weak norm, let's say to measure the convergence probability. So take the soup over bounded elliptic functions with normal less equal than 1 to be bigger than some delta goes to 0 for every delta. Just restating this convergence in probability through that. But essentially what it is saying that if you have perfect model selection, you can do inference as usual in this second stage. Now, what happens that this sounds to be a very good thing, right? Because if I can chase these coefficients properly, if I find them, I can do business as usual. And that's fine, but this is fine only in some applications, in my mind. In some other applications, it might be a little bit delicate. In a sequence of papers, Lieb and Pocher, and this really goes from late 90s until at least 2012, and here are probably 8 or 10 papers. They establish the following negative result. So is there going to be a negative result? So I want to make it the model as simple as possible. So let's look at that model in the case where the error term is normal, and moreover, P, which is the dimension of x, if you want, P equals 1. So only selecting to have one variable or not having that variable. So that's the model. So theorem. So, right, P equals 1. Now, suppose also that the expected value of D and X is different than 0, so they are correlated. By the way, if this does not hold, if they aren't correlated, model selection doesn't play any role. Right? If these guys are not correlated, essentially, whatever you do here does not matter for your inference here. So, but let's assume they are correlated. And suppose star holds. I'm assuming I have the oracle property. It's an assumption. I don't care how you got it. I don't care if you use SCAD, adaptive lasso, whatever you're using, sequence of t-test. I assume you have this thing, which is supposed to be a good thing. Then, the limit as n goes to infinity of the sup of models that's equal to constant probability according to that model Fn minus norm 0, 1 in this norm bigger than delta, and there exists delta bigger than 0 such that does not go to 0. So what's happening here? Now, take the limit. So the sup is not inside the probability, right? So basically, pick a model. Now, you can look at any model which is a pair of alpha and beta naught, which is just a two-dimensional vector now, that has norm at most c, is constant. This limit, now this probability that you're going to converge to normal, that does not go to 0, is bounded away from 0, no matter how many observations you have. So it's a little bit kind of strange, because this is an implication of assuming perfect model selection. I'm assuming I have this event, which is supposed to be a good thing. That's the contradiction of the result. And the proof is not particularly hard. So this is p equals 2, p equals 1. So I have two models only, right? Either I have an alpha, let's say 1, which is computed, which is least squares of y on d alone, if I did not add the variable, or I have y alpha 2, which is the least square estimator of y on d and x. That's the two possible models for every data derivative process. Now, let's consider alpha naught fixed, and then beta naught, actually, I'm going to take a sequence of beta naughts. And I want to do gamma over root n. This is always going to be, I can choose alpha naught, so it's always in this interval. But the result is still true if you do this. If you only look at a small neighborhood of radius root n, the negative result still holds, which is precisely this case. So that the proof goes through for this sequence. So if you look at the limit of the sup over, so let's do the other side, limit of the sup theta is equal to c probability of theta naught of that expression this is at least the limit as n goes to infinity over the sequence I specified for 0 gamma over root n of the same quantity. Make sense? Just fixing a subsequence. Now, that, okay, so delta bigger than delta. Now that is at least the limit n goes to infinity of the probability of the distribution using the first model minus the probability that beta hat n different than 0. So what's the difference from this line to this line? Here I had Fn minus normal. This Fn could be either one of these two models. Now I'm using the first model always, but I'm subtracting the probability that I would actually select the second model. So that gives you a lower bound. Now, this is a very well-behaved model with normality. It's not hard to show, but you need to do some kind of slow calculations. But this probability, because of the oracle property that you select the true model with probability 1, the limit of, theta. The limiting sequence here is alpha naught equals 0, beta naught equals 0. So this is going to converge to P0, 0, beta at n equal to 0. In this model, you do not select because the limit is 0. By the oracle property, this is 0. With probability going to 1, you're going to select the true model. The true model is not to select the x. So this term vanishes, and you are left only with the limit of n going to infinity of the probability of using this first, the estimator using only d bigger than delta. Now, this estimator we actually can compute because it's just the least square estimator of y on d. So if I take a big matrix with all the components of d, this is d transpose d over n minus 1 d transpose y. That's the estimator alpha 1. And I need to subtract this alpha naught and hit by root n. So this is root n d transpose d over n minus 1 d transpose y is just the error term minus d alpha plus d alpha plus x so x beta n, and beta n for us is just gamma over root n minus alpha naught. So this gives you x square root n. D transpose d, there is a over n here, that cancel with this one. And then we get, so the first term is the term we are looking for. The second term gives us alpha naught plus d transpose d over n minus 1 x dx over n gamma over root n minus alpha naught. So these cancel. Because of normality, this is normal to begin with. But we made the assumption that d and x, they are not unrelated. So this does not vanish. This gamma over square root n, because we are hitting by square root n on the outside, it's going to cancel that one. So what this is going to converge to is to a normal with the right variance, but there will be a bias that is essentially expected value of d squared minus 1 expected value of d and x times gamma. So this, if when you look at the different distribution of a normal and this distribution, you can see that you can find a delta that makes those distributions bounded away from each other. Essentially, you omitted a variable, even if the variable is associated with a coefficient that vanish with square root n, because you build a confidence interval which has a square root n that hits it, the square root n cancel, and you get a non-vanishing bias. That non-vanishing bias will destroy your coverage completely. And that's the negative result, essentially. And this holds for the case that you are deciding to add or not add a single variable. There is no reason to believe that this is not going to hold for more complicated models. Right? So, and here is really uniform inference. You want to have confidence regions which are valid uniformly for many data generating processes. What this result is actually telling you is that if you have two data generating processes and you perturb, they are very close, you can see one is a perturbation of the other one, that in the perturbation of the order 1 over root n, so statistically you cannot tell them apart. They look precisely the same. Your confidence regions could work very well for one and terribly for the other one. So that's kind of what's behind it. It's actually a very powerful negative result. And the only really thing that assumes is the oracle property. So that,
I mean, there's something slightly funny that you take a very small dimension.
mm-hmm.
I need to fix the model, but I assume that if you wanted to take a large p, so you consider the usual Lasso set. If you wanted to take a large p and just, if you did things correctly, in the end you'd get the same.
So everything will go through. If I have a huge P, I could create a sequence that has all of the other P's equals to other coefficients equals to 0. They will not matter, and then everything goes through. But but to show a negative result, it holds for even a single variable. That's the striking part. So one could think that, okay, so this is not good. So what if I strengthen this? So what if I do a stronger oracle? Which is, let's take the limit now. If you want to do uniform, well, your oracle better be uniform. Does it make sense? Now I'm just requiring to be uniform as well. And indeed, if this holds, then the limit over the sup of these models and goes to infinity of this probability of our of this post-model selection estimator. Goes to 0 for every delta. Right, so indeed, you achieve that. There is one interesting thing here. So this stronger oracle property implies uniform inference validity. Now, oracle property implies failure of uniform inference. Right? That's what we showed. But strong oracle property implies the oracle property, correct? Because I just put the sup here. Oh, sorry, if. Right? So it's a stronger requirement. So this implies the oracle property, which implies the failure, and this implies that it works, which leads to a contradiction. No such thing exists. If you think the solution was to strengthen the requirement, it cannot be done. That gets out of the window. So if you want really uniform valid confidence regions, you need to let go of oracle property. It's an if and only if procedure. So that's what is called the oracle property. Is the perfect model selection. And it's just the fundamental limit of information, right? What's happening here, that the oracle property, it's estimating as 0, precisely 0, all the coefficients which are not in the support. That's what the oracle property is doing. If any variable not in the support, it's a 0, and I can identify that as a 0. So I'm being super efficient on those components. If I'm super efficient, I can only be super efficient in a 0 measure set of the parameter space. So I will not be able to make it inference valid in a in a good set, in a large set of parameters. So the way we're going to try to get around it is to let go of this property. And so here is one proposal. And actually, in the past few years, and I really mean in the last 3 or 4 years, these ideas start to show up. And please correct me if I'm missing some on the literature, but I think this year there are really a couple of dozen papers being written on this topic now. But let me first go through one procedure, and then next class I discuss the literature, because next class I hope to do the nonlinear models for these procedures. So the idea now is that I have this model y alpha naught d plus x theta naught plus the error term, expected value of the error term given dx equals 0. Let's assume homoscedasticity for now, but that has been relaxed. So what really hurt us is to miss small components. Big components, I'm not going to miss it. I'm going to pick up with any reasonable procedure. So this procedure is called double selection. So step 1, we do Lasso of y on d and x. Step 2, I'll do lasso of d on x. And step 3, here I select a support of x t hat 1. Here select t hat 2. And there are variants of this procedure. We can actually also run just with x here. But let me run with only with x for now. And then in step 3, we run least squares of y on d and the x selected by the first procedure and the second procedure. What's the intuition behind this? So the first, we have our first equation, right? What we're not exploiting by doing model selection here is the fact that we really care about the treatment. Model selection, this equation, which is Lasso, adaptive Lasso, SCAD, all these methods, they were really envisioned for prediction. And a priori, there is no reason to believe that model selection procedures for prediction are actually good as model selection procedures for confidence intervals. There is actually a hidden equation that relates d with x, which is really my concern with confounding factors. If I omit an x that matters with respect to d, I can introduce a bias. That's the potential problem. So there is a hidden equation that relates d and x. A very simple relationship is that d is always the expected value of d given x plus some residual, and the residual is such that satisfies this orthogonal. I can always write this decomposition. So there is nothing that prevents me. And this is just a function of x. So let me make one assumption here, which is not really damaging. I could always add approximation errors. Let's assume that this function is actually x times some gamma naught. Just for simplicity, it's a linear combination. I could have more controls, but these variables, this equation is accounting for the correlation between d and x, which is potentially what can introduce bias. And that's what this is trying to pick up. First step, you pick up things which are good to predict y. Second step, you pick up controls which could introduce extra variables, which could produce omitted variable bias. And as we're going to see, what's going to matter for my final calculation is the product between, so gamma here was the beta, right? Was beta n. Is the product of beta n and the correlation between d and x. If I miss a control in this equation, means that the beta n is small. If I miss the same control in this equation, means that the correlation with d is actually small as well. The compounding factor is the product. There will be conditions under which this product actually is going to be negligible at the root end rate. And that's how we're going to get the result. So how can we analyze this in 15 minutes? Is to first we're going to build up on everything we did in the last 3 classes. I'm going to assume I have some reasonable condition like this. minimum and maximum angle values are good. So I actually have a sparsity of Lasso, and I have good prediction rates. But because sparse angle values are well behaved, this automatically implies L2 norms, convergence, to be S log P over N, and also implies that L1 norm, because I have sparsity, is just a factor of square root S bigger. So I'm going to take those rates for granted because we established them. And that's actually another nice thing of where the literature is at this point. The basics rates for those estimators have been established. Now we can build a lot of new tools which combine Lasso in different ways. We can actually easily now study more complicated estimators. The way I'm going to try to study this is to look at this model and look at the first order conditions of the last step. So the last step is just minimizing y minus d alpha minus x beta, but x only on the support 1, support 2. When you look at the first order conditions, what's going to happen is that 0 equals, so it's going to be, I'm going to write this, the residual. So one way to write this is 1 equals 1 over n, summation of equals 1 to n of the residual, alpha check minus x beta check times di, the vectors of the variables x t hat 1 and t hat 2. That's the first order condition. So since this is a vector of zeros now, I can hit this by any vector I want. In particular, I can hit this by the solution for the second stage, in the second problem. So I'm going to hit by a vector which is gamma hat, which solves step 2. So I get 0 equals to 1 over n, summation 1 to n, yi minus d alpha check minus x beta check times. And actually, I'm going to hit by a vector which is 1 minus that, minus this guy. Hitting, essentially this, I'm going to take the inner product with 1 and minus the solution there. So what I get is di minus x gamma hat. And note that gamma hat is on T2 hat, which is the variables I selected in the second stage. And now we just expand the terms. We get here, we get epsilon minus d alpha check minus alpha naught minus x beta check minus beta naught times this is v minus x gamma check gamma hat minus gamma naught. And now it's going to start some brute force calculations. So we get the first term this is the term that is going to give us actually the leading term for the asymptotic normality minus. So we have alpha check minus alpha naught, summation of d times that thing. D is v plus x gamma naught. Let me do this. D v plus summation plus alpha check minus alpha naught summation of d x gamma x minus gamma naught. So these I took care, and now the third one minus 1 over n over n over n of this third term, summation x v I beta check minus beta naught plus summation 1 over n x beta check minus beta naught x gamma minus gamma naught. So what we're going to have here is the following. I'll take this to the other side. These would be 1 over n summation of dv times alpha check minus alpha naught. That's what I'm really interested on, equals to 1 over n summation of epsilon I. That's going to be my normality term. Now this piece here, it's not hard to show that this third step, we also have beta check. So we get here alpha check, beta check. Alpha check minus beta naught is at most s log p over n, and alpha check minus alpha naught also satisfies s log p over n. So we also have those rates in the third step. And so now plus something of the order. The first term, this is going to give you this piece is going to be square root s log p over n times this n with this whole thing is going to actually also give you the square root of s log p over n. This piece, I'm going to have to bound it by order. It's going to be the L infinity norm of x transpose v times the L1 over n times the L1 norm of beta check minus beta. Yes. Beta not 1 plus order. And this term is actually the prediction norm. You can bound by Cauchy-Schwarz. This becomes the prediction norm for the beta hat and the prediction norm of gamma hat. Essentially. now I'm going to hit everything by root n, because what I really want is the confidence intervals. So I need to hit this by root n times this part. This actually is going to converge d and v. Those are two scalars. This is going to converge to the expected value of d and v. Alpha check minus alpha naught, essentially, plus order 1, but not really little o of 1. And here, this piece actually is going to be 1 over root n, summation of epsilon I vi. That's going to go to normal. 0 mean, and the variance is going to be the associated with that. It's going to be sigma, some sigma square. Alpha. Now, here I have the first term is of order square root n, because I'm hitting with square root n, times this product, which is s log p over n. The second term, this maximum norm of x transpose v over n, that's essentially the penalty term we need to bound. So this piece is square root log p over n. And the L1 norm convergence is square root of s square log p over n. But we still need to hit this by root n. And this last piece, I'm hitting by root n, but I have 2s log p over n times square root s log p over n. And essentially, we get v check minus alpha naught equals to, the first term is the one that's going to go to normal, so that's the good term, plus square root n is going to cancel with one of those. Same thing here is going to be of the same order, plus the order of s log p over square root n. So this goes to a normal 0 expected value of this is the assumption I'm going to need. So I will need essentially s square log square p over n to go to 0. That's kind of what I need to pay in terms of constraining my design. But if this holds, this goes to little order of 1 probability. And just to note that dv, well, this is actually expected value of v plus x gamma naught times v, but v is orthogonal to x. So this expectation of this term is going to be 0, and we get expectation of v square. So we get square root n expectation of v square alpha check minus alpha naught converging essentially weakly to this normal 0 value. And one important thing is that we did that only relying on the rate of Lasso. And the rates of Lasso do not assume perfect selection. They do not make assumption on the separation from zero of the coefficients. So though the rates of Lasso in post-Lasso, they are actually uniformly valid. And that's what translates into this analysis. And then we can get... the crucial thing was really to find this extra set of variables. But by finding this extra set of variables, we are essentially ensuring that we're not going to have the orthogonal property. We're going to probably select a little bit more variables that's going to provide us with the extra adaptivity that we need to achieve uniformity. That's kind of what's behind it. And I apologize, I'm already a little bit late than I'm supposed to. Tomorrow, what I want to do is to push these ideas to nonlinear estimators, talk about logistic regression, quantile regressions, and more generally Z-estimators, and also not do this only for one variable, but if you want to do with P1 variables, where P1 is potentially bigger than that. That's kind of what I hope to touch it tomorrow. Thank you.